please subscribe to support the channel. Wait, wasn't the universe supposed to be 13.8 billion years old? Nailed down, no debate, done? You've heard that number so many times it feels like a law of nature, not something humans calculated from faint microwaves in the sky. So how do we get from that settled number to people talking about a universe that might be 26.7 billion years old? First, how locked in was 13.8? That number comes from a model called lambda cold dark matter, or ΛCDM. Lambda stands for dark energy, the thing that makes cosmic expansion speed up. Cold dark matter is the invisible mass that helps galaxies and clusters form. You put those ingredients into Einstein's gravity equations and you get a recipe for how fast space has been expanding at every moment. Then missions like WMAP and Planck come in. They looked at the microwave background, the faint glow left over from the hot early universe. Across the sky, this glow has tiny temperature bumps and dips. The exact pattern of those bumps depends on how much ordinary matter, and dark energy the universe contains. So cosmologists simulate the universe with different mixtures of those ingredients until the predicted pattern matches the observed one as closely as possible. When they get the mix right, they don't just get some rough age, they get a specific expansion history, how the expansion rate changed over billions of years. From that, they compute how long it has taken to go from an extremely dense early state to the size and expansion rate we see today. That time span is what we call the age of the universe, and in this standard model, it lands at about 13.8 billion years with less than 1% uncertainty. But what does it actually mean to calculate that age? Cosmologists describe the size of the universe with a single number that changes with time, called the scale factor. It tells you how far apart galaxies are compared to today. Right now, by definition, that factor is set to 1. In the past, it was smaller, and close to the Big Bang, it was extremely small. The expansion rate is how fast this scale factor is changing. The equation that controls that rate is called the Friedmann equation. In words, it says the square of the expansion rate is proportional to the total energy density in the universe, plus terms for spatial curvature and the cosmological constant. Energy density here means how much stuff per volume in ordinary matter, dark matter, radiation, and dark energy. Each component thins out differently as the universe expands. If you know those rules, you can work out how the expansion rate changes with time. Once you have that, getting the age is a matter of adding up tiny time steps. You mathematically run the expansion backwards, shrinking the scale factor from 1 down to 0, and at each step, you use the Friedmann equation to say how much time passes. You add those steps from scale factor basically 0 to scale factor 1. The result is a single number, the age of the universe in years. That's where the 13.8 comes from. If that were the only line of evidence, you'd be right to be suspicious. So cosmologists use independent cross-checks. One big one is the distance ladder. You start with nearby stars whose distances you can measure directly using parallax. Then you calibrate pulsating stars called Cepheids. Their pulsation period tells you their true brightness. Compare that to how bright they look and you get their distance. Cepheids then calibrate Type Ia supernovae, which act as standard candles at much larger distances. With that chain, you can measure distances to faraway galaxies by how bright those supernovae look, and compare that to their redshift, the amount their light is stretched while traveling through expanding space. This gives you another way to map how fast a universe has been expanding at different times. When you fit an expansion history to those distances and redshift data, you again get a universe that is about 13 to 14 billion years old. There's another check. When astronomers map the three-dimensional positions of millions of galaxies, they see a preferred separation scale in how galaxies cluster, a bump in the statistics. That scale comes from sound waves that move through the hot plasma of the early universe, called baryon acoustic oscillations. The physical size of that scale is set by early universe physics, so it acts like a standard ruler at different redshifts. Measure where that ruler shows up in the galaxy distribution and you get another test of the expansion history. Fit those data with the ΛCDM model, and you get an age that again lines up with about 13.8 billion years. And then there's the age of the oldest objects inside the universe. If we ever found a star that was clearly older than 13.8 billion years, the standard picture would be in serious trouble. Astronomers have pushed hard on this by studying old stars like HD 140283 and the oldest globular clusters. Early estimates made it look like some of these might be older than the universe, but as measurements and models improved, their ages dropped back into a range that fits under the cosmological age. Put all of that together and you can see why cosmologists were confident. Microwave background measurements, the distance ladder, galaxy clustering and baryon acoustic oscillations, and the ages of the oldest stars all told a consistent story. ΛCDM fit enough data that it earned the label concordance model. For years, if you had walked into a cosmology conference and said the universe might be almost twice as old, most people would have parked that idea in the speculative corner. So here's the tension that ramps up the stakes. If this picture is so tightly woven, how can anyone seriously suggest a universe that's 26.7 billion years old without tearing the whole thing apart? What exactly would you have to change about expansion, redshift, and even the basic equations to make that number work? To answer that, you first need to see how we connect the current expansion rate, redshift, and the universe's age. Once you understand that machinery, you'll see why changing the age isn't just swapping one number for another. It's rewriting the entire expansion history from the Big Bang to today. How do you even measure the age of something that contains everything, including the clock you're using to time it? Let's start with the part you can actually observe: galaxies moving away from you and the way their light gets stretched. Take a galaxy and split its light into a spectrum. You see familiar patterns of lines from elements like hydrogen and oxygen. In a lab, those lines sit at specific colors. In distant galaxies, those same lines are shifted towards the red end of the spectrum. That shift is called redshift. The bigger the shift, the more the light got stretched while traveling through expanding space. Edwin Hubble took that seriously in the 1920s and 1930s. He measured redshifts, turned them into speeds, estimated distances to galaxies, and plotted speed versus distance. He saw a rough straight line. Farther galaxies have larger recession speeds. The slope of that line is what we now call the Hubble constant. It tells you how many kilometers per second of recession speed you get for each megaparsec of distance. The key detail is the unit. The Hubble constant has units of 1/time. When you flip it, you get a time scale. If the universe had always expanded at the current rate, from zero size to now, the age would just be roughly the inverse of the Hubble constant. That simple inverse gives you a ballpark age of the universe. That was the first hint that the universe had a finite age, and that you could actually estimate it from data. But here's the first big catch. The universe has not expanded at one steady rate. Gravity pulls everything together. Dark energy pushes everything apart, and their relative importance changes over time. So why isn't the age just 1 over the Hubble constant? And what do you do instead? In the early universe, matter and radiation densities were much higher. That means gravity had a stronger braking effect on expansion, slowing it down more than it does today. Later, as the universe expanded and matter thinned out, dark energy started to dominate and made expansion speed up. So the expansion rate has changed, first slowing harder, then easing up, and finally accelerating. Because of that, just taking today's expansion rate and inverting it is too simplistic. Cosmologists handle this by modeling the entire expansion history. They write down how the expansion rate depends on the densities of matter, radiation, curvature, and dark energy. Each of those components decreases with expansion in a specific way. Matter density drops with volume, radiation drops with volume and also with redshift of photon energy. Dark energy stays about constant if it behaves like a cosmological constant. Once you know how the expansion rate depends on the size of the universe, you can calculate the total age. In words, you add up little time slices as the universe grows from very tiny to its current size, with each slice determined by the current expansion rate at that size. That adding process, done numerically with real data for the density parameters, gives the 13.8 billion year result in the standard model. Not just one over the Hubble constant, but a carefully integrated history. So where does the Hubble constant actually come from in practice? And why is it now such a headache that people are even willing to talk about radical ideas like a 26.7 billion year universe? You can get the Hubble constant in two pretty different ways. The first way is what people sometimes call the early universe route. Here, you use the cosmic microwave background and assume the lambda cold dark matter framework. You fit the pattern of temperature fluctuations in that microwave background, and the best fit parameters of the model give you a value for the Hubble constant today. That number comes out around the high 60s in the usual units. The second way is the late universe route. This uses distance ladder measurements of nearby galaxies, Cepheid variables, and Type Ia supernovae. You calibrate the distances step by step, then look at how supernovae brightness relates to redshift, and fit a Hubble constant directly from relatively local data, without relying heavily on the early universe microwave background. That gives you a number in the low 70s. These are not tiny differences. The error bars on both methods have shrunk, but the two preferred values stubbornly disagree beyond what those errors should allow. That disagreement is what people call the Hubble tension. On top of that, there are other late universe methods, like strong gravitational lens time delays, that also weigh in. They probe different distances and redshifts, but again, tend to land closer to the higher late universe values. So now you have a situation where the early universe method plus the standard model says one thing, the late universe methods seem to say another, and both sides claim precision. That naturally raises the question, is the model we're using to connect redshift, distance, and time missing something? At this point, it's tempting to think, fine, let's just pick a different age like 26.7 billion years and move on. But that's not how the math works. Why can't you just dial the age up like a volume knob and keep everything else the same? Because the age of the universe is not a free label. It is the result of the entire expansion history. If you say the universe is almost twice as old, you're saying that the way the scale factor grew with time was different at every stage. The universe must have expanded more slowly on average than in the standard picture to take that much extra time to reach its current size and expansion rate. That has consequences. A different expansion history changes how redshift relates to time. It changes when structures like galaxies and clusters could form. It changes how long light has been traveling from a given redshift. And it changes how all the major observables line up. The cosmic microwave background, the supernova distance redshift relation, the baryon acoustic oscillation scale, and the statistics of large-scale structure. So anyone claiming an age of 26.7 billion years is not just suggesting a new number. They're proposing a new mapping between redshift, distance, and time. They're modifying the equations that govern expansion, sometimes even suggesting changes to how fundamental constants behave or how light loses energy over long distances. And they have to do that while still reproducing the same high-precision data that made 13.8 billion years look so solid in the first place. So that is why the idea is so extreme. It's not about tweaking a parameter inside an accepted model. It's about rewriting the expansion history from the first fraction of a second after the Big Bang all the way to now, and insisting that the new story still fits all the measurements we already have. So the next natural question is, what observation was strong enough to push anyone to try something so drastic? What did we actually see that made some researchers think we might need a completely stretched timeline where galaxies have way more time to grow up? To answer that, you have to look at what James Webb Telescope started to find in its first deep images. Extremely distant galaxies that look way too massive and evolved for a 13.8 billion year universe. How can a universe that's only a few 100 million years old already be packed with big, complex galaxies that look like they've had a long life? That's the uncomfortable question JWST dropped on cosmology almost as soon as it started sending data home. When JWST took its first deep images, astronomers went hunting for the most distant galaxies they could find. Distance in this context means redshift, how much the wavelengths of light have been stretched. They started seeing candidates at redshifts around 10, 12, even up toward 15. In the 13.8 billion year model, that corresponds to a universe that's roughly 300 to 500 million years old. So far, so good. That's cosmic dawn, exactly where you expect to see the first serious galaxies starting to show up. The shock comes from what those galaxies seem to be. Some of them don't look like tiny baby systems. Estimates from their light suggest stellar masses of hundreds of millions to tens of billions times the mass of the Sun, plus pretty high rates of ongoing star formation. That's not just a few stars turned on early. That's big, bright, already doing serious galaxy business in what's supposed to be the universe's first half-billion years. So where's the problem exactly? Simulations based on the standard lambda cold dark matter model already know how to form massive galaxies quickly. You start with dark matter halos, gas falls in, stars form, feedback from supernovae and black holes blows gas out and stirs things up. In the most optimistic cases, you can build big galaxies surprisingly fast, but the JWST candidates push that machinery hard. They look too big, too well assembled, and in some cases too chemically enriched given how little time the standard timeline says they've had. The phrase that started popping up was impossible early galaxies. And JWST isn't the first hint that early structure might be too grown up. Before JWST, ALMA and other observatories had already found oddballs like ALSS 073.1, a galaxy whose light has been traveling for about 12.5 billion years. That puts it at a time when the universe was only around 1.2 billion years old in the standard picture. Yet, it shows a regularly rotating disk and a massive central bulge, features you normally associate with much more mature galaxies. In other words, it looks like something that should have taken several billion years to settle, but it appears very early. So are these galaxies truly impossible, or are we just underestimating how wild the early universe can be? That's where the argument starts. Some researchers say nothing truly breaks yet. You can push the standard model by assuming star formation in those early halos is extremely efficient, that early stars were on average heavier than today's stars, that dust properties are different, and that some of the early mass estimates are biased high. In that view, JWST is forcing us to update how we think about early star formation, not throw away the entire cosmology. Others aren't so relaxed. They point out that to keep everything inside ΛCDM, you end up dialing parameters to the edge. Star formation running almost as fast as physically allowed, black holes growing at the maximum permitted rate, and very rapid metal enrichment. It's not impossible, but it starts to look like the universe chose the most aggressive options everywhere, just to keep our model happy. When a theory only survives by pushing every knob to the limit, people start wondering if the theory is missing something deeper. And the debate is very much ongoing. Teams have published papers with titles basically saying, "No tension, calm down" for galaxies beyond redshift 10, showing that with updated assumptions, you can squeeze them into ΛCDM. Other teams respond that once you fold in all the data, including quasars and gamma ray bursts, the early universe still looks uncomfortably busy. Right now, it's not a clean, this kills the model situation, but it's also not just a tiny technical glitch you can brush aside. JWST has upgraded the problem from a curiosity to something the field has to take seriously. So what do you do if galaxies at very high redshift look too old and too massive for a 13.8 billion year universe? One very direct idea is maybe we've given them too little time. Instead of changing how galaxies form inside the standard timeline, change the timeline itself. That's the move that leads to the 26.7 billion year proposal. Rajendra Gupta's model is built precisely around this issue. He takes the claim seriously that some high redshift galaxies are as evolved as galaxies we usually think took 8 to 10 billion years to grow. If that comparison is even roughly right, then a universe that's only a few 100 million years old at those redshifts doesn't give you enough time. So his approach is to stretch the mapping between redshift and age. In his framework, the same redshift that standard cosmology calls 300 million years after the Big Bang becomes several billion years after the Big Bang. Now those galaxies no longer have to assemble at breakneck speed. They can grow over billions of years at more normal rates. In numbers, the difference is huge. In the usual model, a galaxy at redshift 10 sits at about 500 million years after the Big Bang. In Gupta's model, that same redshift is closer to 5.8 billion years. A redshift of 20, which normally means around 180 million years after the Big Bang, becomes roughly 3.5 billion years. So the impossible early galaxies stop being early in terms of time. They're only early in terms of redshift. The universe has simply been evolving for much longer than we thought before their light reaches us. That's the door JWST cracks open. Once you see galaxies that seem overgrown for their spot on the standard timeline, you have two options. Either galaxy physics is more extreme and efficient than your simulations assumed, or the timeline itself is wrong and needs to be stretched. Most researchers are still betting on the first option. Gupta and a few others are exploring the second, more radical one. Which raises the next big question. What does a model have to do, mathematically, to stretch the universe's age to 26.7 billion years and still not break all the other data? How do you actually change redshift time conversion that much without trashing the microwave background and the supernova results? That's where the Rebel model comes in. Tired light plus changing fundamental couplings all stitched together into a new framework that claims to fix the early galaxy problem and double the age of the universe. What kind of person looks at the entire universe and says, I think it's actually twice as old as everyone believes? That's where Rajendra P. Gupta comes in. He's an astrophysicist at the University of Ottawa. In 2023, he published a paper in the journal Monthly Notices of the Royal Astronomical Society called JWST Early Universe Observations and ΛCDM Cosmology. In that paper, he looks at the James Webb early galaxy data and basically says standard lambda cold dark matter needs very extreme assumptions to make these galaxies fit, and that's a warning sign the model might be missing something big. His starting point is simple. JWST is seeing very compact, very massive galaxies at redshifts around 15 that, in the standard timeline, exist just a few 100 million years after the Big Bang, but look as evolved as galaxies that have had 10 billion years to grow. If that's true, he argues, you either need absurdly fast galaxy formation, or you admit that the age redshift conversion might be wrong. His paper tries the second option. Keep the observations, keep an expanding universe, but change the physics that turns redshift into cosmic time. Others aren't so relaxed. They point out that to keep everything inside ΛCDM, you end up dialing parameters to the edge. Star formation running almost as fast as physically allowed, black holes growing at the maximum permitted rate, and very rapid metal enrichment. It's not impossible, but it starts to look like the universe chose the most aggressive options everywhere just to keep our model happy. When a theory only survives by pushing every knob to the limit, people start wondering if the theory's missing something deeper. And the debate is very much ongoing. Teams have published papers with titles basically saying, no tension, calm down, for galaxies beyond redshift 10, showing that with updated assumptions, you can squeeze them into ΛCDM. Other teams respond that once you fold in all the data, including quasars and gamma-ray bursts, the early universe still looks uncomfortably busy. Right now, it's not a clean this kills the model situation, but it's also not just a tiny technical glitch you can brush aside. JWST has upgraded the problem from a curiosity to something the field has to take seriously. So what do you do if galaxies at very high redshift look too old and too massive for a 13.8 billion year universe? One very direct idea is, maybe we've given them too little time. Instead of changing how galaxies form inside the standard timeline, change the timeline itself. That's the move that leads to the 26.7 billion year proposal. Rajendra Gupta's model is built precisely around this issue. He takes the claim seriously that some high redshift galaxies are as evolved as galaxies we usually think took 8 to 10 billion years to grow. If that comparison is even roughly right, then a universe that's only a few 100 million years old at those redshifts doesn't give you enough time. So his approach is to stretch the mapping between redshift and age. In his framework, the same redshift that standard cosmology calls 300 million years after the Big Bang becomes several billion years after the Big Bang. Now, those galaxies no longer have to assemble at breakneck speed. They can grow over billions of years at more normal rates. In numbers, the difference is huge. In the usual model, a galaxy at redshift 10 sits at about 500 million years after the Big Bang. In Gupta's model, that same redshift is closer to 5.8 billion years. A redshift of 20, which normally means around 180 million years after the Big Bang, becomes roughly 3.5 billion years. So the impossible early galaxies stop being early in terms of time. They're only early in terms of redshift. The universe has simply been evolving for much longer than we thought before their light reaches us. That's the door JWST cracks open. Once you see galaxies that seem overgrown for their spot on the standard timeline, you have two options. Either galaxy physics is more extreme and efficient than your simulations assumed, or the timeline itself is wrong and needs to be stretched. Most researchers are still betting on the first option. Gupta and a few others are exploring the second, more radical one. Which raises the next big question. What does a model have to do, mathematically, to stretch the universe's age to 26.7 billion years and still not break all the other data? How do you actually change redshift time conversion that much without trashing the microwave background and the supernova results? That's where the Revel model comes in. Tired light plus changing fundamental couplings all stitched together into a new framework that claims to fix the early galaxy problem and double the age of the universe. What kind of person looks at the entire universe and says, I think it's actually twice as old as everyone believes? That's where Rajendra P. Gupta comes in. He's an astrophysicist at the University of Ottawa. In 2023, he published the paper in the journal Monthly Notices of the Royal Astronomical Society called JWST Early Universe Observations and ΛCDM Cosmology. In that paper, he looks at the James Webb early galaxy data and basically says standard lambda cold dark matter needs very extreme assumptions to make these galaxies fit, and that's a warning sign the model might be missing something big. His starting point is simple. JWST is seeing very compact, very massive galaxies at redshifts around 15 that in the standard timeline exist just a few 100 million years after the Big Bang, but look as evolved as galaxies that have had 10 billion years to grow. If that's true, he argues, you either need absurdly fast galaxy formation or you admit that the age redshift conversion might be wrong. His paper tries the second option. Keep the observations, keep an expanding universe, but change the physics that turns redshift into cosmic time. Now for the headline shock number. In Gupta's hybrid model, the age of the universe comes out to about 26.7 billion years instead of 13.8. That's not a tiny tweak, that's almost a factor of 2. He gets this by combining two ideas: covarying coupling constants and a modified tired light effect. Covarying coupling constants means fundamental interaction strengths, like gravity and electromagnetism, are allowed to change slowly as the universe expands. Tired light means that photons lose a small amount of energy as they travel on top of the usual stretching of space. But together, these effects change how redshift builds up with distance and time, and that changes the clock you use for the universe. The easiest way to see how drastic this is to compare ages at fixed redshift. In standard cosmology, a redshift of 20 corresponds to roughly 180 million years after the Big Bang. In Gupta's CCC plus tired light model, that same redshift maps to about 3.5 billion years. Standard cosmology puts redshift 10 at around 500 million years. Gupta's model puts it at roughly 5.8 billion years. So when you see a galaxy at redshift 10, the standard model says this thing formed incredibly quickly in the first half-billion years. Gupta's model says, no, this galaxy had almost 6 billion years to assemble before its light left it. It's the same redshift, same photons, but a completely different age calendar. That directly feeds into the problem he wants to fix. In the standard picture, some JWST galaxies look like they built up tens of billions of solar masses and stars, reached high metal content, and formed central black holes in just a few 100 million years. To make that happen inside ΛCDM, you end up reaching for extreme ideas, very massive first-generation stars that form and explode rapidly, black holes that grow at or above the usual theoretical limits, or special features in the spectrum of early fluctuations that seed huge structures very early. These are not impossible, but they're definitely edge-of-the-envelope scenarios. Gupta's claim is that if the universe is actually 26.7 billion years old, you don't need those extremes. You can stick with more ordinary star formation and black hole growth rates. A galaxy that looked too massive for 300 million years becomes perfectly reasonable if it had a few billion years to gather gas, form stars, and recycle material. His model is designed so that when you compute distances and brightnesses for Type Ia supernova using this new redshift time relation, you still match the big Pantheon plus supernova dataset just as well as ΛCDM does. In other words, he's trying to show, I can keep the supernova fits, keep an expanding universe, explain the small angular sizes of those early galaxies, and simultaneously give them more time to grow. That's why you see covarying coupling constants plus tired light repeated in discussions of his work. The covarying part is the idea that fundamental constants like the speed of light or Newton's gravitational constant evolve in a coordinated way with the scale factor of the universe. The tired light part adds a small extra redshift as photons propagate. The net effect is a universe that still expands, still has a big bang, but accumulates redshift differently. Distance versus redshift curves, age versus redshift curves, all get reshaped. When he refits the supernova data with this framework, the best fit solution lives in a universe that's almost twice as old. Now, what are the stakes if something like this turned out to be right? It wouldn't just be the universe is older, cool trivia. It would mean the standard interpretation of redshift is incomplete. Right now, mainstream cosmology treats cosmological redshift as almost entirely due to the stretching of space itself. Gupta's model says a small but important part also comes from photons gradually losing energy, in a way inspired by old tired light ideas, but embedded inside an expanding universe. On top of that, letting coupling constants evolve means the strengths of fundamental forces may not be fixed numbers, but slow functions of cosmic time. That's a very deep change. And then there's the question of dark matter and dark energy. In follow-up work, Gupta goes further and argues that if you allow these evolving couplings and the tired light contribution, you might not need dark energy at all, and maybe not even dark matter in the usual sense. Instead, the effects we attribute to those components would come from how the effective gravitational and other couplings change over time, and from how light accumulates redshift. In that picture, what we currently call dark energy and dark matter are byproducts of us assuming constants really are constant. If he's right, almost everything about the content of the universe would be reinterpreted. So this is not a small proposal. It challenges three pillars at once: the standard age of the universe, the idea that redshift is purely from expansion, and the idea that dark matter and dark energy are separate physical substances. That's why most cosmologists treat it as a bold, speculative alternative rather than a new standard. To accept 26.7 billion years, you'd have to give up a lot of things that currently fit together very well. Which leads straight into the next hard question. This whole idea leans heavily on tired light, a concept most cosmologists have basically discarded for decades. So what exactly is tired light? Why was it abandoned? And how is Gupta trying to bring it back in a new form? How can the universe look like it's expanding, but some of the redshift might not be from expansion at all? That's the weird door the old tired light idea tries to open. Tired light goes back to the 1920s, to Fritz Zwicky. At that time, people were still trying to understand why galaxy spectra were so strongly redshifted. One option was the expanding universe picture. Space itself stretches, so light waves get stretched and their wavelength increases. Zwicky suggested another possibility. Maybe you don't need the galaxies to be racing away. Maybe photons just lose a tiny bit of energy as they travel huge distances through space. Less energy means longer wavelength, which shows up as a redshift. In tired light language, redshift is light wearing out over billions of light years. The farther the photon travels, the more energy it loses, the more its color shifts toward the red. The basic idea is simple. Redshift is proportional to distance because photons are slowly drained as they go, not because space is stretching everywhere. That was attractive in an era when the idea of expanding space still felt strange. On the surface, that sounds like it could explain Hubble's law. If the energy loss per unit distance is fixed, then a photon that travels twice as far loses twice as much energy. That gives you a roughly linear relation between redshift and distance, which is what Hubble saw. You don't need curved space-time or a global expansion, just light gradually losing energy in some still unknown way. So why didn't tired light win? Because once better data arrived, it started to fail test after test. First problem, supernova brightness. Type Ia supernovae are used as standard candles. In an expanding universe, when you look at higher and higher redshift, there is a specific way their brightness should decline with distance once you include both geometry and expansion. Tired light models predict a different brightness redshift curve. When people actually measured lots of supernovae, the data lined up with the expansion curve, not with tired light. Second problem, the cosmic microwave background. The microwave background is extremely close to a perfect black-body spectrum. That means the distribution of photon energies follows a very specific shape. In an expanding universe, you can take a hot black-body spectrum and stretch all the wavelengths by the same factor, and it stays a perfect blackbody, just colder. Tired light mechanisms tend to distort the spectrum because photons lose energy in a way that is not equivalent to uniform stretching of space. Getting a perfect blackbody under tired light is very hard without adding a lot of extra assumptions. Third problem, time dilation. In an expanding universe, high redshift events should appear time-stretched. A distant supernova light curve should evolve slower by a factor related to 1 plus the redshift. That time dilation has been measured. Supernovae and quasar variability at high redshift really do appear slowed down the way expansion predicts. Classic tired light models don't naturally give that. If redshift came only from photons losing energy, the clock of the event itself wouldn't stretch the same way, so you wouldn't see the correct time dilation pattern. When you put all of that together, tired light just couldn't keep up. It was a creative idea for its time, but data from supernovae, the microwave background, and detailed galaxy surveys pushed it out of the mainstream. Cosmologists stuck with the expanding universe explanation for redshift because it matched a lot more observations with fewer arbitrary tweaks. So why is tired light even back in the conversation now? This is where Gupta's approach is different. He's not trying to bring back the old tired light universe where there is no expansion. Instead, he keeps an expanding universe but adds a tired light-like contribution on top. In his picture, part of the redshift still comes from space itself expanding, just like in standard cosmology. But there is an extra term, a small energy loss as photons travel through the cosmic environment. You can think of it like this. When a photon leaves a distant galaxy and travels to us, two things happen. First, the space it travels through stretches, making its wavelength longer. Second, in his model, it also loses a little energy in a way that scales with distance traveled or with the properties of the medium it moves through. The key point is that this extra redshift changes how you translate observed redshift into distance and time since the Big Bang. For a given observed redshift, If part of it is this tired light effect, the amount of expansion needed to reach that redshift is smaller. Less expansion needed for the same redshift means the universe could have taken longer to get there. That's how you can keep the same redshift measure but stretch the corresponding age from hundreds of millions of years to several billion years. So because he keeps expansion in the model, Gupta can still plug into a lot of the standard machinery. You still have an evolving scale factor. You still have an early hot phase. You still have structure formation. The tired light term is an extra effect that modifies the distance redshift and age redshift relations without completely throwing away the Friedman-style expansion picture. Now connect this back to the impossible JWST galaxies. In standard ΛCDM, a galaxy at redshift around 10 sits in a universe that's about 500 million years old. To reach the observed stellar mass, metal content, and compact structure in that short time, you need extremely rapid star formation and very efficient assembly. It's doable only if a lot of parameters are pushed to their limits. In Gupta's hybrid model, the same redshift 10 galaxy could correspond to something like 5.8 billion years after the Big Bang. That's an order of magnitude more time. In that much time, you can form multiple generations of stars at normal or moderately enhanced rates. Those stars can live, die, and enrich the gas with heavy elements. Gas can cool, collapse, and settle into the dense structures JWST sees. Black holes can grow by steady accretion instead of only by extreme bursts. Suddenly, masses that looked crazy for 300 or 500 million years become fairly ordinary for several billion years. So the tired light term isn't just a random complication. In this framework, it's the trick that lets you say, these galaxies aren't freakishly fast, our cosmic clock has been miscalibrated. The light from a redshift 10 object hasn't just crossed a rapidly expanding young universe, it's crossed a slower, older universe where photons pick up extra redshift as they go. And that combination buys you a much longer history before that light ever reaches your telescope. But tired light on its own still isn't enough to remake the universe. To really stretch the timeline and try to get rid of things like dark energy and even dark matter, Gupta adds another ingredient, the idea that the strengths of the fundamental forces themselves slowly change across cosmic time. That raises the next question. What does it actually mean for a coupling constant to change, and how can playing with those numbers reshape the whole expansion history of the universe? What if the constants of nature aren't actually constant and the whole history of the universe is stretched because the rules have been slowly drifting? That's the core of this next move. In particle physics, every force comes with a setting strength. Those settings are called coupling constants. For electromagnetism, one of the key ones is the fine structure constant, usually written as alpha. It's just a number that tells you how strongly charged particles interact with light. Gravity has its own constant, the gravitational constant, which sets how strong gravity is between masses. In standard physics, these numbers are treated as fixed. They don't depend on where you are or when you measure them. They're baked into the laws. Gupta's proposal says, what if that assumption is only approximately true, and only true locally? What if, on the scale of the whole universe and over billions of years, these couplings slowly change in a coordinated way as the universe expands? Not wildly, not jumping around, but drifting in a specific pattern tied to the size of the universe. That's the covarying coupling constants part. The couplings vary together with the cosmic scale. This sounds radical, but the basic idea isn't completely new. Back in the mid-20th century, Paul Dirac looked at some odd coincidences between large dimensionless numbers in physics and suggested that maybe some constants actually change with cosmic time. His thought was that as the universe ages, certain fundamental ratios might evolve, and what we call constants are just their values right now. That idea never became mainstream, but it stayed in the background as a possible direction if data ever demanded it. Gupta grabs that old thread and stitches it into cosmology. In his framework, quantities like the effective gravitational strength and other couplings are allowed to scale with the expansion of the universe. As the scale factor grows, the couplings follow specific rules that he writes down. You don't need the equations here, but the key consequence is this. If the couplings change, the equations that control the expansion rate also change, because those equations depend on how strong gravity is and how different components of the universe behave. In the standard picture, the expansion rate at any moment is set by the total energy density in matter, radiation, dark energy, and any curvature. Each of those terms scales with the size of the universe in a fixed way. If you now let the couplings depend on the scale, those scalings shift. Matter might not affect expansion in exactly the same way at early times as it does at late times. Gravity might effectively act stronger in the past and weaker now, or vice versa, depending on the exact rules you choose. Let's spell out what that does to expansion history. Suppose gravity is effectively stronger in the early universe. That would tend to slow the expansion more back then, pulling matter together more efficiently, helping structure form. Later, if the effective gravitational coupling weakens, gravity's braking power decreases, and the universe can expand more freely. That late-time loosening can imitate some of the effects we currently attribute to dark energy making expansion accelerate. So with evolving couplings, you can do two things at once. You can change how fast structures like galaxies and clusters grow at early times, and you can also change how quickly expansion speeds up at late times, without necessarily putting in a separate dark energy fluid in the usual way. Combine that with the tired light contribution to redshift, and you get a very different mapping between redshift, distance, and time than in ΛCDM. From your point of view as an observer, this shows up as follows. You measure a certain redshift from a distant object. In the standard model, you turn that into a distance and an age using fixed couplings and expansion-only redshift. In Gupta's model, that same redshift is partly from expansion, partly from energy loss, and the expansion history itself is modified by the changing couplings. So the distance and the age you infer for that redshift can be very different, even if the observed redshift is identical. That's how the age at a given redshift can jump from hundreds of millions of years to several billions. Of course, you can't just wave your hands and say, the constants change, and call it a day. To be taken seriously, the model has to be pinned down mathematically and tested against data. Gupta's CCC plus tired light framework isn't just a vague concept. He writes explicit formulas for how the couplings scale with the size of the universe, plugs them into the expansion equations, and then computes what observers should see for things like supernova brightness and baryon acoustic oscillation distances. He then fits those predictions to real datasets. A big one is the Pantheon Type Ia supernova sample, which contains over 1,000 supernovae across a wide range of redshifts. In standard cosmology, you choose parameters like the matter density and dark energy density to make your distance redshift curve pass through those points. Gupta does something similar, but with his expanded set of parameters that include how couplings vary and how strong the tired light effect is. The claim is that with a particular choice of these new parameters, his model fits the supernova data as well as the standard ΛCDM model does, but with a very different age for the universe, about 26.7 billion years. On top of that, he compares to baryon acoustic oscillation measurements, which give another handle on distances at various redshifts. Again, he argues that his CCC plus tired light predictions can be brought into agreement with those constraints without breaking the fits, all while keeping the extended age. That's the part that makes cosmologists pay attention even if they're extremely skeptical. If this were just a toy idea that obviously failed against basic data, it would be easy to ignore. But a model that is tuned to match key observations yet gives such a different interpretation of what redshift and age mean forces people to at least look closely. It might still fall apart when you test it with more detailed data, but you can't dismiss it purely on the grounds of it obviously doesn't fit anything. At the same time, the amount of freedom you introduce by letting couplings vary and adding tired light terms is huge. That's exactly why critics worry about fine-tuning and overfitting. If you're allowed to reshape the expansion equations and tack on extra redshift contributors, of course you can bend the model to hug certain datasets. The real question is whether it holds up under the full weight of all cosmological observations, not just supernovae and a handful of distance probes. And that leads to the next big piece of the story. What exactly is this rebel model challenging? To understand how disruptive a 26.7 billion year universe would be, you need to see just how successful the standard ΛCDM model already is, and why replacing it takes more than just explaining some early galaxies. How hard is it to actually beat the standard model of the universe? Let's look at what Gupta's 26.7 billion year idea is going up against. In modern cosmology, ΛCDM is the baseline. The recipe is simple to state. About 5% of the universe is ordinary matter, atoms, gas, stars, planets, you. Roughly 27% is cold, dark matter, some non-luminous stuff that clumps, gravitates, and builds the skeleton of structure. The remaining 68% is dark energy, represented in the equations as a cosmological constant, usually written with the Greek letter lambda. Those three components, plus general relativity, define ΛCDM. Lambda plus cold dark matter. What makes ΛCDM powerful isn't just that it sounds neat on paper. It's that this mix, when you put it into Einstein's equations and evolve it forward, matches an incredible range of observations with a small set of parameters. You use it once and it explains several completely different things at the same time. The flagship success is the cosmic microwave background. When you run ΛCDM and compute what the small temperature variations in that background should look like, you get a pattern of peaks and troughs as a function of angular scale. Those are signatures of sound waves moving through the hot plasma of the early universe. The observed pattern from satellites like WMAP and Planck line up with the ΛCDM prediction to high precision. Not just vaguely similar, peak positions, heights, and shapes all match extremely well when you choose a specific combination of matter, and dark energy. Then you move to large-scale structure. Start the universe with tiny initial density fluctuations, evolve them under gravity in a ΛCDM background, and you get a web-like pattern of filaments and clusters. When you compare that to galaxy surveys that map millions of galaxies in 3 dimensions, the statistics of the real universe, how clumpy it is on different scales, match what ΛCDM gives you. So the same model that nailed the microwave background is also getting the cosmic web broadly right. On top of that, Type Ia supernovae distances line up with ΛCDM's prediction for an accelerating universe. When teams in the late 1990s measured supernovae at different redshifts, they found that distant ones were dimmer than they would be in a universe that was just coasting or slowing down. ΛCDM with a cosmological constant explains that cleanly. Dark energy starts to dominate a few billion years ago, and expansion speeds up. Even earlier in time, Big Bang nucleosynthesis, the process that formed light elements like helium and deuterium in the first few minutes, is also consistent with ΛCDM. If you plug in the baryon, or ordinary matter density that ΛCDM uses to fit the microwave background, and then ask what should be the primordial abundances of helium and deuterium be, you get values that agree with what we actually measure in very old, nearly pristine gas clouds. So you've now linked first few minutes physics to 380,000 years after the Big Bang to billions of years, with one unified picture. This is why cosmologists take ΛCDM so seriously. It's not some fragile construction balanced on one weird dataset. It's a compact model that passes test after test across cosmic time. When something does that, the default assumption is not throw it out, it's any anomaly has to be really solid before we consider replacing this. But it's also true that ΛCDM is not perfect. The most famous issue right now is the Hubble tension. If you infer the Hubble constant, the current expansion rate, from the microwave background using ΛCDM, you get a value around the high 60s in the usual units. If you measure it directly in the local universe using the distance ladder, you get a value around the low 70s. The difference is only a few kilometers per second per megaparsec, but the quoted uncertainties are small enough that this mismatch is statistically significant. It looks like more than just random noise. That doesn't automatically kill ΛCDM, but it hints that either some systematic error still hides in one or both methods, or the model might need some extension. Maybe a slightly different early universe energy component, maybe a twist in dark energy, maybe something else subtle. There are also small-scale issues. ΛCDM works extremely well on large scales, but when you zoom in to the level of individual galaxies and their satellites, you hit puzzles. Simulations predict more small dark matter halos than we see as satellite galaxies, missing satellites problem, and some predicted subhalos should be dense enough to host bright satellites that simply aren't observed. Too big to fail problem. Galaxy rotation curves and the detailed distribution of dark matter inside halos raise more questions. Many of these can be adjusted by adding messy baryonic physics, star formation, feedback, gas outflows, but they keep the door open to the idea that maybe dark matter physics is more complicated than cold and collisionless, or that gravity might need modification at some level. Still, notice the pattern. These are tensions and open questions, not outright contradictions. Every time we find a weird dwarf galaxy or a surprising cluster, the first response is to see if better simulations or more complete data bring things back in line. So far, ΛCDM has bent but not snapped. Now, put yourself in the shoes of any alternative model, including Gupta's 26.7 billion-year universe. It's not enough to say, I can explain JWST's early galaxies better and call that a win. To actually replace ΛCDM as the standard, a new model has to do at least as well on all the other things ΛCDM already matches. That means it has to produce a cosmic microwave background with acoustic peaks in the right places with the right relative heights. It has to give a distance redshift relation that fits the full supernova data, not just a subset. It has to reproduce baryon acoustic oscillation measurements as a function of redshift. It has to be consistent with Big Bang nucleosynthesis and the measured primordial element abundances. It has to generate a large-scale structure power spectrum that looks like what we see in galaxy surveys and weak lensing measurements. And it has to not obviously violate local tests of gravity and constraints on variations of fundamental constants. Only after clearing that bar can a model even start to claim that its extra features, like a much older universe or no dark matter, are a genuine improvement instead of just extra complexity. So when someone says, maybe the universe is 26.7 billion years old, the question from the community is not just, does that help with JWST galaxies, but do you still pass all the brutal precision tests ΛCDM passed? That's why this debate is so intense. The 26.7 billion year idea isn't fighting a weak opponent. It's challenging a model that has explained nearly everything from the first 3 minutes to the present day with remarkable success. To win, it has to keep all those victories and then solve more problems on top. And that brings us to one of the most sensitive parts of the standard model, dark energy. If you stretch the age of the universe and change how gravity behaves, what happens to this mysterious component that seems to drive acceleration? Do you still need it at all? That's the next move in Gupta's proposal. Reinterpret cosmic acceleration in a way that tries to erase dark energy from the picture and still keep a 26.7 billion year universe. How do you make the universe speed up without adding a new kind of energy to it? That's the core fight over dark energy in an older universe picture. In the standard ΛCDM story, dark energy is very simple. It behaves like a cosmological constant. That means its density per unit volume stays roughly the same as the universe expands. Space doubles in volume, you get twice as much dark energy. Matter thins out as things spread apart, radiation thins and loses energy as wavelengths stretch, but dark energy just sits there, same density everywhere. As the universe grows and matter becomes more diluted, dark energy takes over the energy budget. That happens a few billion years ago, and from then on, its repulsive effect dominates, and the expansion rate starts increasing instead of slowing down. Right now, in that standard picture, about 68% of the total energy content of the universe is this dark energy. Ordinary matter is only about 5%, dark matter about 27%. Dark energy is not something we see directly, we infer it because the distances to supernovae, the pattern of the microwave background, and the clustering of galaxies all point to a universe whose expansion has been accelerating for the last several billion years. If you fit that data with Einstein's equations and you don't include some form of dark energy, the curves just don't match. Gupta's later work tries to flip that logic on its head. He asks, what if the thing we're calling acceleration is not a sign of a new energy component, but a sign that we misinterpreted redshift and gravity? In his framework, you still have an expanding universe, but two extra effects are in play. First, the tired light contribution we already talked about. Photons pick up extra redshift as they travel, losing a little energy along the way, on top of the stretching from expansion. Second, the strengths of fundamental forces, including effective gravity, are allowed to change with the expansion. As the universe grows, the couplings evolve in a coordinated way. Put those together and the apparent acceleration can be a kind of mirage. The distance-redshift relation you infer under the assumption of fixed couplings and redshift from expansion only will look like expansion is speeding up. But if in reality redshift has extra contributions and gravity is weakening over time, the universe might not be accelerating in the standard sense. It might be expanding under a different rule that just mimics acceleration when you interpret the data with ΛCDM glasses on. Here's the key move. The Hubble diagram, the plot of distance versus redshift you build from supernovae, doesn't know what microphysics you use to compute it. It's just points. This redshift, this brightness. ΛCDM fits those points with a model that includes dark energy as a constant density component. Gupta's model says, keep the same points, but instead of inserting dark energy, let couplings vary and add tired light. Then solve the modified expansion equations and see what curve you get. By tuning how quickly couplings change and how strong the tired light term is, he claims you can produce a curve that passes through the same supernova points and stays consistent with baryon acoustic oscillation distances. But because your expansion rate is generally slower and your redshift has extra contributions, the total time needed to go from early hot conditions to the present is much longer. Now the universe needs about 26.7 billion years to get where we are, instead of 13.8. That's the mathematical trick that buys you the extra age. You haven't changed the observed redshifts or brightnesses. You've changed the model that maps those observables to a history of the scale factor and to a total time since the Big Bang. In the standard picture, the same data force you into a relatively young universe with dark energy. In Gupta's picture, they're reinterpreted as a sign of evolving couplings and tired light in a much older universe. On paper, that sounds neat. No mysterious dark energy, more time for galaxies to grow, and a consistent fit to key distance measurements. But there's a cost, and this is where the skepticism ramps up. In ΛCDM, dark energy isn't just a fudge term thrown in to fit one dataset. It is constrained by multiple independent lines of evidence. Supernovae tell you something about the late-time expansion. The cosmic microwave background tells you about the geometry and energy content at early times. Baryon acoustic oscillations give you a standard ruler to track expansion in between. Weak gravitational lensing and structure growth measurements tell you how fast matter clumps over time. When you put all of those together, a picture with a cosmological constant fits surprisingly well. If you remove dark energy, you don't just point at the supernova plot and say, I can fit this differently. You also have to explain why the microwave background peaks sit where they do, why the inferred geometry looks nearly flat, why structure growth over billions of years matches what we see in galaxy surveys and lensing data, and why local tests of gravity don't show obvious variations. Every one of those checks is a constraint on how much you're allowed to play with couplings and redshift mechanisms. That's why a lot of cosmologists see models like Gupta's as very high risk. You're trading one big unknown, dark energy, for several moving parts, evolving couplings, a tired light term, and a reshaped expansion history. The question isn't, can you fit supernovae and some BAO points? It's, can you do that and still pass all the other tests with the same level of precision as ΛCDM? So far, the standard model has been through that gauntlet. Alternatives are only starting to run it. And remember, stretching the age to 26.7 billion years and dropping dark energy doesn't just change late-time expansion. It ripples into everything: structure formation, the timing of reionization, the way the cosmic microwave background encodes early physics. The more you adjust the rules, the more places there are where the universe can come back with nope. So, if dark energy might be on the chopping block in this older universe picture, what about dark matter, the other big invisible ingredient in ΛCDM? Gupta goes even further there, suggesting that once you change the age, the couplings, and the redshift mapping, you might not need dark matter either, at least for some of the big cosmological effects. That raises the tension again. Can a 26.7 billion year universe really get away with deleting both dark energy and dark matter and still match all the evidence we have? How do you remove something that seems to show up in almost every cosmology observation we have? That's the scale of what you're trying to do when you say, maybe there is no dark matter. In the standard picture, dark matter is not optional. It's built into the way structure forms in the universe. You start with tiny density fluctuations in the early universe. Dark matter, which doesn't interact with light, begins to clump first because it only feels gravity. Ordinary matter falls into those dark matter clumps later, cools and forms stars and galaxies inside them. Without that invisible scaffolding, you don't get the right pattern of galaxies and clusters we see today. On the scale of individual galaxies, dark matter explains why stars in the outer regions orbit faster than you would expect from the visible mass alone. If you just add up the light and gas and use ordinary gravity, the outer parts of galaxies should rotate more slowly and in some cases even fly apart. Instead, their rotation curves flatten out. The standard fix is a large halo of dark matter surrounding the galaxy, adding extra gravitational pull. On the scale of clusters of galaxies, dark matter shows up again. The total mass you infer from how fast galaxies move inside the cluster is much larger than what you get from visible matter. Gravitational lensing, where clusters bend and distort light from background galaxies, also reveals more mass than you can see. And when you look at the cosmic microwave background, the pattern of hot and cold spots depends strongly on how much dark matter and ordinary matter there is. The best fit models consistently point to something like cold dark matter making up about 27% of the universe's energy budget. So dark matter is not just a patch for one weird dataset. It appears in rotation curves, cluster dynamics, lensing maps, structure formation, and the microwave background all at once. That's why it's a central part of ΛCDM. Now pivot to Gupta's stronger claim. In his follow-up work, once he has the 26.7 billion year framework in place with covarying coupling constants and a tired light contribution, he goes further and argues that you might not actually need dark matter either, at least for some of the big cosmological effects. The idea is that if gravity effectively changes its strength over time and redshift is partly due to photons losing energy, some of the phenomena we currently attribute to dark energy and dark matter can be reinterpreted as consequences of those modified rules plus the stretched age. In that view, the older universe gives structure more time to grow even without a large cold dark matter component. The evolving couplings change how gravity acts over large scales and long times, so the growth rate of cosmic structures, the timing of clustering, and even some aspects of galaxy dynamics could come from modified dynamics rather than a separate dark matter fluid. Tired light and the changed expansion history then help match distance measurements without invoking dark energy. This is a very bold move. You're not just changing one part of the model, you're trying to shift the explanation for cosmic acceleration and large-scale structure away from both dark energy and dark matter and onto modified gravity, evolving couplings, and an older timeline. It's an attempt to reduce the number of unknown substances at the cost of complicating the underlying physics and expansion history.
Here's the reality check.
Dark matter is woven into a huge range of independent observations. You see its fingerprints in galaxy rotation curves across many different galaxy types, the detailed lensing patterns of massive clusters, including famous systems where two colliding clusters show the gas separated from the main mass peaks, the way structure grows in numerical simulations. Add cold dark matter and you get something that looks like the real cosmic web. Remove it and the match falls apart. The heights and positions of the peaks in the microwave background power spectrum, which depend on how baryons and dark matter interact gravitationally in the early plasma. Any model that claims no dark matter has to reproduce all of those signatures with something else. It's not enough to say, I can fit supernova distances or I can stretch the age. You need a consistent alternative that explains why clusters lens light the way they do, why the bullet cluster type systems look the way they look, why rotation curves behave as observed over a huge mass range, and why the cosmic microwave background still ends up with the same structure. That's an enormous challenge. Modified gravity ideas have been tested for years, and while some of them can explain specific features like galaxy rotation curves without dark matter, they usually struggle with clusters or the microwave background, or they require extra components that start to look a lot like dark matter again. Gupta's model is dropping itself into the middle of that difficult territory and claiming that with evolving couplings, tired light, and an older universe, you can get away without dark matter and dark energy. That's why the scrutiny is intense. Zoom out and look at what's at stake. At this point, it isn't just a question of whether the universe is 13.8 or 26.7 billion years old. You're talking about the basic identity of 95% of the cosmos. In ΛCDM, that 95% is dark matter plus dark energy. We don't know what they are, but we see their effects everywhere. In Gupta's proposal, a big part of that 95% might instead be a sign that our assumptions about constant couplings, pure expansion redshift, and standard gravity are wrong when you look at the entire history of the universe. If Gupta is right, we've been misreading redshift, mislabeling the source of cosmic acceleration, and misinterpreting the signals that led us to dark matter. If he's wrong, ΛCDM holds its ground again. But the early galaxy puzzle doesn't disappear. We still have to explain how those JWST galaxies got so big and mature so fast inside a 13.8 billion year universe. And that brings us to the next piece of the story. What actually happens to early galaxies if you give them all that extra time? How different does the early universe look when z equals 10 means billions of years after the Big Bang instead of just half a billion? How different does the early universe look if you quietly add 10 billion extra years to the clock? This is where the numbers in Gupta's model really hit you. Start with the basic comparison. In standard ΛCDM, if you look at a galaxy at redshift 10, the universe is only about half a billion years old at the time that light left it. At redshift 20, it's roughly 180 million years old. Those are tiny fractions of the total 13.8 billion year age. They're supposed to be the very first chapters after the Big Bang, when structure is just getting going and the first serious galaxies are forming. In Gupta's CCC plus tired light model, the same redshifts map to completely different ages. Redshift 10 is not half a billion years after the beginning. It's about 5.8 billion years. Redshift 20 is not 180 million years. It's more like 3.5 billion years. You've taken what used to be infant universe snapshots and turned them into middle-aged universe snapshots. Same observed stretching of light, totally different timestamps. Now think about what that means for building galaxies. In ΛCDM, if you want a galaxy at redshift around 10 to have a stellar mass of roughly 10 billion times the mass of the Sun, you have to compress a lot of work in less than a billion years. Dark matter halos have to grow very fast. Gas has to fall in quickly, cool efficiently, and turn into stars at a very high rate. Feedback from supernovae and young stars can't blow too much gas away or you won't build enough mass. Everything has to be tuned to produce a big, bright system in record time. That is why those JWST galaxies raised eyebrows. Some of the mass estimates suggest systems with tens of billions of solar masses in stars already in place at redshift about 10 or higher. To get that in ΛCDM, you push star formation efficiency towards the upper limits. You let gas accrete extremely fast, and you may even need special conditions in the initial density field to seed very massive halos early. It is not impossible, but it is definitely aggressive. Shift to a 26.7 billion year universe and redo that story. Now a redshift 10 galaxy has almost 6 billion years to build its stars. That is comparable to the time our own Milky Way had between its early formation and intermediate stages. With billions of years to work with, you can achieve 10 billion solar masses in stars using fairly ordinary star formation rates and normal duty cycles. You do not have to demand that every early halo is operating at maximum efficiency all the time. Gas can flow in, form stars, get blown out, cool again, and repeat over many cycles. In that stretch timeline, the phrase impossible galaxy loses most of its force. A system that looked shockingly massive for 500 million years looks completely reasonable for several billion years. You do not need exotic star formation laws or extremely top-heavy stellar populations just to hit the observed mass by that redshift. The early universe starts to look less extreme and more like a scaled version of later cosmic epochs. Now add in metallicity and dust, which are another part of the tension. When astronomers look at some high redshift galaxies, they see signs of relatively high metal content and significant amounts of dust. Metals here just mean elements heavier than helium: carbon, oxygen, iron, and so on. These are not produced in the Big Bang. They are made inside stars and spread into the surrounding gas when those stars die. To get a high metal content, you need several generations of stars. First generation, mostly hydrogen and helium. They live, explode, and seed the gas with heavier elements. Second generation forms from that enriched gas, making more metals. Over time, repeated cycles raise the metallicity. Dust forms from these heavy elements and from the outflows of certain types of stars. Spreading that dust and metal-rich gas through a galaxy also takes time, through winds, supernova explosions, and mixing processes. In standard ΛCDM, doing all of that by 300 to 500 million years after the Big Bang is very tight. You need the first stars to form very early, be very massive, live fast, and die quickly, and then you need extremely efficient recycling into new star generations in a short time window. Again, not impossible, but definitely at the edge of what seems comfortable. In a 26.7 billion year universe, those same metallicities and dust levels stop being a rush job. If a redshift 10 galaxy is actually almost 6 billion years into cosmic history, there has been plenty of time for multiple stellar generations to live and die. Metals can accumulate, dust can build up, and gas can be mixed across the system. What looked like this galaxy is enriched way too early becomes this galaxy has had several billion years to process its gas, which is not surprising at all. So from Gupta's perspective, the extended age solves two connected problems at once. Mass buildup is easier and chemical evolution is easier. The galaxies that strain ΛCDM's early time schedule become ordinary products of long, repeated cycles of star formation and feedback. But here's the key point you need to feel. This is the attractive part of the older universe idea, and it is exactly why most cosmologists are trying very hard to see if they can fix the problem without touching the cosmic clock. If you are a working cosmologist or galaxy formation person, you have two levers you can pull. One lever is galaxy physics, star formation efficiency, how stellar feedback works, how easily gas cools in low metallicity environments, how often you get very massive first-generation stars, and how fast black holes can grow. These areas are messy, full of uncertainties, and definitely need better modeling. Tweaking them is painful but expected. This is the fix the knobs inside ΛCDM route. The other lever is cosmology itself. Rewrite how redshift maps to time, let fundamental constants vary, add tired light terms, maybe remove dark matter and dark energy. This is a much more drastic move. If you pull this lever, you are not just adjusting how one class of simulations works. You are changing the global framework that explains almost every major cosmological observation we have. So most of the community would rather push galaxy physics models very hard before they start tearing into the backbone of ΛCDM. Rebuilding our understanding of star formation, feedback, and early black hole growth is a big job, but it doesn't force you to re-explain the cosmic microwave background, Big Bang nucleosynthesis, and all the precision tests of gravity at once. Rebuilding the entire universe's expansion history does. That is the philosophical split you should have in mind. An older universe with extra time makes JWST's early galaxies feel safe and comfortable, but at the price of shaking almost everything else. A younger universe forces those galaxies into a high-pressure, high-speed origin story, but keeps the rest of the cosmological framework intact. So the next question is obvious. If you try to double the age of the universe, can you really keep the toughest constraint of all intact, the cosmic microwave background? Or does that precise relic of the early universe smash the 26.7 billion year idea the moment you push on it? How do you double the age of the universe without wrecking the one measurement that pins down early history better than anything else we have? That's the wall any 26.7 billion year model slams into, the cosmic microwave background. The CMB is not just a colorful wallpaper image. It's a snapshot of the universe when it was a hot plasma everywhere, at a redshift around 1,100. In the standard ΛCDM model, that corresponds to about 380,000 years after the Big Bang. At that moment, the universe had just cooled enough for electrons and protons to combine into neutral atoms. Photons suddenly stopped bouncing off free electrons all the time and could travel freely. Those photons are what we see today as the CMB. Across the whole sky, the CMB is almost the same temperature, but not perfectly. There are tiny fluctuations, a few parts in 100,000 hotter or colder. When you analyze those fluctuations, you don't just look at them by eye. You decompose the sky into angular scales and measure how strong the fluctuations are at each scale. That gives you a power spectrum, a curve with a series of peaks and troughs. Those peaks come from sound waves in the early plasma. Before recombination, gravity tries to pull matter in while radiation pressure pushes out. That push-pull sets up oscillations. Different scales are caught at different stages of compression or rarefaction when the photons decouple. The first peak, second peak, third peak, their positions and heights all depend on how much ordinary matter, dark matter, and radiation there is, and on the geometry of space. ΛCDM nails this spectrum. When you choose a particular set of parameters, matter fraction, dark energy fraction, the overall curvature, and you run the standard calculation, you get a predicted spectrum. That spectrum matches the data from missions like Planck at a crazy level of detail. Not just roughly similar. The peak positions line up, the relative heights are right, the small-scale damping tail behaves as expected. This is one of the tightest tests in all of cosmology. So, if you come in with a 26.7 billion year universe, you cannot just say, I changed the age and ignore the CMB. You must still produce a universe that, at redshift 1,100, looks the same statistically. The same sound horizon scale, the same angular size of that scale on the sky, the same pattern of acoustic peaks. If you slip too far, the CMB data will crush your model immediately. Gupta's CCC framework tries to handle this by being careful about where the big changes happen. The idea is not to rewrite the early universe completely. Instead, the modifications to the metric and the covarying couplings are designed so that at very early times, the behavior looks close enough to ΛCDM to give you a CMB that's compatible with what Planck sees. The really dramatic changes, the slower late-time expansion, the different redshift time mapping, the strong effect of tired light, are supposed to kick in mainly at lower redshifts, long after recombination. In simple terms, you keep the early movie mostly the same up to the CMB frame, then you change how the movie runs afterwards and how you interpret the timestamps on each frame. That way, you can still have a recombination era with the right physics to produce the observed acoustic peaks, but you can reinterpret how long ago that era actually was in terms of total cosmic time. The redshift of the CMB, around 1100, stays the same, but the age at redshift 1100 can be stretched in the new model compared to the standard 380,000 years. On paper, that gives you a path. Leave the early time observables mostly intact, change the late time mapping, and try to keep everything that touches the CMB safe while you adjust distances and ages at lower redshift to fix JWST galaxies and supernova tension. This is exactly where a lot of cosmologists remain unconvinced. The ΛCDM fit to the CMB isn't just good, it's insanely precise. There isn't much room to move the parameters around without messing up peak positions or relative heights. When you start changing the underlying theory, the metric, the way couplings behave, the way redshift builds up, you're effectively changing the entire calculation behind that spectrum. To claim success, it's not enough to say the model can, in principle, be made consistent with the CMB. You have to actually run the full calculation compared to the Planck data and show that the residuals are as small as in ΛCDM. Right now, most of Gupta's work is focused more on supernovae, JWST galaxies, and large-scale distance measures. That's where he shows detailed fits. For many experts, the big unanswered question is, does CCC plus tired light really match the CMB with the same precision, or is it only guaranteed to be roughly compatible at a broad level? Because the CMB is so precise, any deviation has to thread a very narrow needle in parameter space. You have to tweak the couplings and metric enough to change late-time distances and ages substantially, while barely disturbing the early-time physics that sets the acoustic peaks. That's a hard balancing act. Until someone demonstrates that full consistency with the CMB at Planck's level, skepticism is going to stay high. Looking ahead, the CMB is not done tightening the screws. Future experiments are aiming for even more detailed measurements of polarization patterns and small-scale anisotropies. Polarization carries extra information about the velocity fields at recombination. Small-scale measurements reveal how photons scattered, how matter clumped, and how light was lensed on the way to us. Any subtle difference between ΛCDM and an alternative model like CCC plus tired light can show up there as tiny distortions. If those future CMB observations keep lining up with ΛCDM and leave almost no room for deviations, models that rely on big changes to gravity or redshift mechanisms will get squeezed harder. On the other hand, if we start seeing systematic mismatches, odd polarization patterns, small-scale features that don't quite fit, that could be a sign that the underlying framework needs modification and that some of these exotic ideas aren't just mathematical games. Either way, the CMB is the referee nobody can avoid. It locks down the early universe so tightly that any 26.7 billion year scenario has to show it can play by those rules while still reinterpreting the later phases of cosmic history. But the CMB is only part of the story. Even if you somehow thread that needle, you still have to deal with the main rulers of the late universe, Type Ia supernovae and baryon acoustic oscillations, the measurements that map out how expansion has changed over time. So the next question is, in this older universe framework, can you really match those distance measurements as cleanly as ΛCDM does, or are you just fitting a few curves while ignoring the full weight of the data? How can two totally different universes tell you the exact same story when you look at exploding stars and ripples in galaxy maps? That's the strange part about this 26.7 billion year idea. Start with the supernova side. Pantheon is a huge compilation of Type Ia supernovae, more than 1,000 of them spread over a wide range of redshifts. Each Type Ia is used as a standard candle. You know its true brightness after calibration, you compare it to how bright it looks, and from that you get a distance. Put distance and redshift together for all those supernovae, and you get a detailed map of how expansion has changed over time. In standard ΛCDM, you take your parameters, matter density, dark energy density, curvature, Hubble constant, and generate a theoretical curve of distance versus redshift. When you lay that curve over the Pantheon points, it fits very well. That's one of the reasons cosmologists are confident the universe has been accelerating for the last few billion years. The supernovae are dimmer at a given redshift than they would be in a constantly slowing or coasty universe. Gupta takes the same Pantheon dataset and runs a different game. Instead of saying, keep gravity constant and add dark energy, he says, let coupling constants evolve, add a tired light term, and change the expansion history. Then he tunes his new parameters so that his CCC plus tired light universe, with an age of 26.7 billion years, can match the supernova data about as well as ΛCDM does, even though the underlying physics is very different. Now jump to the other main ruler. Baryon acoustic oscillations, BAO for short. These are the frozen echoes of sound waves from the early universe. Before recombination, matter and radiation were coupled, and pressure waves rippled through the plasma. When the universe cooled enough for atoms to form and photons to decouple, those waves stopped, leaving a preferred physical separation scale between overdense regions. Today, when you map galaxy positions in 3D, you see a slight excess of pairs separated by that characteristic scale, roughly a few 100 million light-years. That BAO scale acts like a standard ruler. You know its physical size from early universe physics, you measure how large it appears in redshift and angle at different cosmic epochs. That tells you how the universe expanded between then and now. Again, ΛCDM uses its parameter set to predict these distances. And again, the predictions line up with measurements from surveys like BOSS, eBOSS, and others very nicely. Gupta's model can't ignore BAO either. If you change couplings and expansion, you risk changing both the physical sound horizon scale in the early universe and how that scale projects to what we see today. So his framework is built and tuned so that when you calculate BAO distances in the CCC plus tired light setup, you still get something compatible with the galaxy data. The idea is that by choosing how fast couplings evolve, you can preserve the effective BAO scale while remapping how redshift corresponds to actual age and distance. Here's the key point. When you take all these distance indicators, supernovae, BAO, sometimes strong lens time delays, and you plot them as distance versus redshift, a lot of different theoretical curves can be made to run through the same cloud of points if you give yourself enough parameters to adjust. That is what people mean by degeneracy. One curve comes from a 13.8 billion year ΛCDM universe with dark matter and dark energy. Another can come from a 26.7 billion year universe with evolving couplings and tired light. On the distance redshift graph, they both look good if you tune them correctly. But underneath those curves, the stories are completely different. In ΛCDM, redshift is almost entirely the result of expanding space. The age at a given redshift is fixed by integrating the standard expansion equations. Dark matter and dark energy are separate components that drive structure formation and late time acceleration. In Gupta's model, part of redshift is from photons losing energy, the strength of gravity and other forces changes with time, and you don't need dark energy in the usual sense. Same data points, very different explanation. So how do you decide which universe is real when both can hug the same distance measurements? You don't just stare at the Hubble diagram longer. You look for other signatures that are harder to fake. Cosmologists check whether the models start to diverge in more subtle redshift-dependent ways. For example, how fast does structure grow as a function of time? Does the predicted rate of clustering or the growth factor match what we see from galaxy surveys and weak gravitational lensing? Do strong lens time delays, where light from a background quasar takes multiple paths around a massive galaxy, pick out one expansion history over another? You also hit them with internal consistency tests. Take parameters inferred from the CMB and see if they still make sense when you use them to predict BAO and supernova results in the same model. Make sure the age you inferred doesn't break Big Bang nucleosynthesis or local constraints on how constants can vary. The standard ΛCDM model has gone through a lot of that and still holds together. Alternatives like CCC plus tired light are just starting that process. So far, ΛCDM passes more of these cross-checks, which is why it remains the default. The upshot is this. Fitting the Pantheon plus supernova data and BAO distances is necessary, but not enough for a 26.7 billion year universe to be taken seriously as a replacement. The challenge is to survive everything else at the same time. Until an older age model can do that demonstrably, it stays in the interesting but speculative category. Meanwhile, one of the loudest tensions that push people toward alternatives in the first place is the mismatch in the Hubble constant between early and late universe methods. So the next question is, does a 26.7 billion year universe really help with the Hubble tension, or is it just adding more knobs without giving a clear, testable win? How can the same universe tell you two different stories about how fast it's expanding right now? That's the heart of the Hubble tension, and it's one of the reasons people are even entertaining something as extreme as a 26.7 billion year cosmos. Here's the mismatch in plain terms. When you infer the Hubble constant, h0, from the cosmic microwave background using the standard ΛCDM model, you get a value around 67 to 68 kilometers per second per megaparsec. That means every megaparsec of distance adds about 67-68 kilometers per second of recession speed. But when you measure h0 directly in the nearby universe using the distance ladder, Cepheid variables calibrating Type Ia supernovae, you get something closer to 73 kilometers per second per megaparsec. The difference is only a few units, but the error bars on both sides are now so small that this 5 to 9% gap is statistically significant and has survived multiple new datasets, reanalyses, and cross-checks. It just doesn't go away. In ΛCDM, both numbers should be the same. h0 is a single global parameter, the current expansion rate. The early universe method, CMB, and late universe methods, distance ladder, strong lensing, etc., are supposed to be just different ways of measuring the same thing. The fact that they disagree this much is why people call it a tension instead of just annoying noise. So where does a model like CCC plus tired light come in? The key move is that it changes how you connect redshift, distance, and time. In the standard picture, cosmological redshift is almost entirely due to expansion. Space stretches, wavelengths stretch, and the amount of stretching tells you about the scale factor of the universe when the light was emitted compared to now. Once you assume that and you adopt ΛCDM's fixed couplings and energy content, a given redshift, together with other observables, locks in a particular distance and a particular h0. In Gupta's framework, redshift is not purely from expansion. Part of it comes from photons losing energy as they travel, the tired light component, and the expansion itself is governed by couplings that change with time. That means the same observed redshift can correspond to a different distance, and the way distances evolve with redshift can differ from ΛCDM even if your distance redshift curve for certain probes looks similar over a specific range. In principle, this gives you extra freedom to relieve the Hubble tension. You can have an expansion history where the effective h0 inferred from early universe data, when interpreted with the new model, is closer to what you get locally while still fitting the same CMB and supernova data points. You're basically saying the reason the early and late methods disagree under ΛCDM is that ΛCDM is using the wrong mapping between redshift, distance, and time. Use the CCC plus tired light mapping instead, and the apparent disagreement can shrink or vanish. But this extra flexibility comes with a big risk: overfitting. Every time you add a new ingredient, evolving couplings, tired light terms, modified metric functions, you add more knobs you can turn. More knobs make it easier to bend your model so that it matches a particular dataset like the distance ladder or the CMB. That doesn't automatically mean the physics is correct. It just means you have more parameters to soak up discrepancies. The serious test is not, can I tweak my parameters until the Hubble tension goes away? The serious test is, does my tweaked model then make clear predictions that differ from ΛCDM, and do new observations land on my side or on ΛCDM's? If all your extra complexity just serves to erase current anomalies without giving sharp new predictions, you're not really solving the problem, you're just adding dressing to it. This is why a lot of cosmologists are cautious. ΛCDM already has a relatively small set of parameters and still explains a huge amount of data. A model that adds evolving couplings and tired light effects to fix the H0 mismatch and stretch the age has to earn that complexity. It has to do more than just fit as well. It needs to either fit significantly better overall or predict distinctive signatures that we then actually see. And this is where future H0 measurements become a kind of lie detector for both ΛCDM and any 26.7 billion year universe. Right now, the main tension is between CMB inferred H0 and distance ladder H0, but new, more independent methods are coming online. One is gravitational wave standard sirens. When two neutron stars or black holes merge, they send out gravitational waves whose waveform tells you their absolute luminosity distance directly from the physics of the merger. If you can also get a redshift for the host galaxy from electromagnetic observations, you get a Hubble constant measurement that doesn't rely on the usual distance ladder or the CMB. Others are improved strong lens time delays. In some systems, a distant quasar is lensed by a foreground galaxy, and you see multiple images. The light paths have different lengths, so brightness variations arrive at slightly different times in each image. Those time delays depend on the geometry of the universe and directly on H0. Better lens modeling and larger samples can give a very precise H0 without using supernovae or the CMB. If those independent tools keep landing on the higher local value, that pushes pressure onto ΛCDM and makes alternatives more attractive. If they instead line up with the CMB inferred H0, that supports ΛCDM and makes it harder to justify radical frameworks that were mostly motivated by the Hubble tension. And if they land somewhere weird in between, then both the standard model and its challengers have to rethink their assumptions. Either way, these upcoming measurements will not care how elegant a model sounds. They'll spit out distances and redshifts, and whichever cosmology handles all the data with fewer arbitrary knobs and better internal consistency is going to win. The Hubble tension is not just a number mismatch, it's a stress test for how far we have to bend our theories to accommodate new precision data. And even if a 26.7 billion year universe could massage the Hubble problem, there's another huge test waiting: how structures grow over time. If you nearly double the cosmic age and change gravity, what happens to the growth of the cosmic web, and can you still end up with the same pattern of galaxies and clusters we see today? How different does the cosmic web look if the universe has almost twice as long to build it? That's the question you have to answer before you can take a 26.7 billion year universe seriously. In the standard ΛCDM model, structure growth starts from tiny density ripples in the early universe. These ripples come from quantum fluctuations stretched to cosmic scales in the very early phase, often tied to inflation. At first, the fluctuations are tiny, 1 part in 100,000. Gravity then slowly amplifies them. Wherever the density is slightly higher than average, gravity pulls in more matter, and those regions collapse into dark matter halos. Ordinary gas falls into those halos, cools, and forms stars and galaxies. Over time, small halos merge into bigger ones, building up groups, clusters, and the cosmic web of filaments you see in simulations. People actually test this picture by running huge numerical simulations. You start with a 3D box filled with dark matter particles whose initial positions and velocities match the predicted fluctuation spectrum from the early universe. Then you let gravity evolve the system for 13.8 billion years in a ΛCDM background. Simulations like Millennium, Illustris, Eagle, and many others do exactly this, often adding hydrodynamics to follow gas, stars, and black holes. The end result is a distribution of matter that looks very similar to what galaxy surveys find. clusters, voids, filaments, and a power spectrum of clustering that matches observations pretty well. That's a big validation of ΛCDM's timing and growth history. Now, imagine you change the total age of the universe to 26.7 billion years. Even before you modify anything else, basic intuition says if gravity has almost twice as long to act, structures can grow more, small fluctuations can be amplified further, halos can merge more times, galaxies have more time to assemble mass and settle into mature configurations. In that kind of stretched timeline, you can relax some of the pressure on early galaxy formation. In ΛCDM, to get very massive galaxies by redshift 10, you need the initial fluctuations that seed those halos to be in the high tails of the distribution, and you need the growth rate and star formation efficiency to be very high. In a 26.7 GYR universe, you can start with less extreme initial overdensities and let them grow for longer. The same final halo mass is easier to reach. The same stellar mass can build up with more moderate star formation rates spread over more time instead of extremely intense bursts packed into a few 100 million years. So extra time does help. It makes the early galaxy speedrun problem easier to solve. But to claim victory, you can't just say, we have more time, so it's fine. You need to actually compute how structures grow in this new cosmology and compare the full pattern to what we observe. And here's the gap. Right now, we don't have massive, high-resolution cosmological simulations run in Gupta's exact CCC plus tired light framework the way we do for ΛCDM. The work so far is mostly analytic and semi-analytic. It looks at background expansion, fits distance measures like supernova and BAO, and discusses implications for early galaxies in a more qualitative or simplified way. It does not yet offer the same level of brute force tests where you evolve billions of dark matter and gas particles for a 26.7 GYR history and generate a synthetic universe to compare with real surveys. That means for structure formation, the 26.7 GYR universe is still a sketch. You can see how the extra time and modified gravity could reduce tension with JWST's early galaxies, but you don't yet have the detailed cosmic web predictions that exist for ΛCDM. Until someone runs those full simulations, you don't know if the older universe can reproduce the exact shape of the matter power spectrum across scales, the abundance of clusters and massive halos at different redshifts, the statistics of galaxy environments, void sizes, and filament thickness. If those predictions come out by a lot, the model fails regardless of how nicely it handles early galaxies. So what would count as a real smoking gun in favor of a stretched timeline universe for structure formation? You'd need something like this: a clear, reproducible mismatch between ΛCDM predictions and observations that persists even when you throw your best galaxy formation physics at it. And that mismatch is naturally explained by CCC plus tired light with its different growth history. For example, maybe the measured matter power spectrum on some range of scales has a feature ΛCDM can't reproduce with extreme tweaks, but the CCC plus TL growth equations produce it automatically. Or maybe the evolution of cluster abundance with redshift systematically disagrees with ΛCDM, but fits better under the older age model. Or perhaps higher-order statistics, like how clusters and filaments connect, show a pattern that clearly points to a different growth history. Right now, we don't have that level of evidence. Most large-scale structure observations are broadly consistent with ΛCDM, once you include reasonable uncertainties in baryonic physics and measurement systematics. That doesn't mean ΛCDM is perfect, but it does mean any alternative has to be very carefully tested before claiming a win. So at this stage, for structure formation, the 26.7 GYR universe is more of a promise than a proven upgrade. If you give me more time and modified gravity, I can make early massive galaxies easier. That's interesting, but it's not yet a full demonstration that the entire cosmic web prefers this stretched timeline over the standard one. And structure is only one part of the early universe story. If you double the age and change how gravity behaves, you also change when the first stars ignite and how the universe transitions from neutral gas to the ionized state we see today. That whole era, from the first stars as z equals 20 to 30 to the completion of reionization around z equals 6, is what people call cosmic dawn. Now take that same set of redshifts and drop them into a 26.7 GYR universe. The redshift numbers themselves don't change. We still observe z equals 20, z equals 10, z equals 6. What changes is the age that those redshifts correspond to. In Gupta's CCC plus tired light mapping, z approaching 20 is something like 3.5 billion years after the Big Bang, not 180 million. Redshift 10 is around 5.8 billion years, not about half a billion. Redshift 6 is now much later too. The entire cosmic dawn era stretches out enormously in terms of actual time. That has big consequences. Instead of cramming the whole reionization process into a few 100 million years, you can spread it out over a few billion. The first stars can form, enrich their surroundings, die, and be followed by multiple generations in the same halos. Early galaxies can go through many more cycles of gas inflow, star formation, and feedback. Black holes that start as a few tens or hundreds of solar masses can grow to supermassive size more calmly, without needing extreme accretion rates right up against theoretical limits. So a stretched timeline makes reionization and early black hole growth feel less like a race and more like a long campaign. But again, you don't get to just stretch the clock and call it good. Reionization leaves fingerprints that we've already measured, and those fingerprints have to look the same in any viable model. One key probe is CMB polarization. When the universe reionizes, free electrons appear again in large numbers, and CMB photons can scatter off them. That scattering imprints a specific polarization signal on large angular scales, and effectively measures the thickness and timing of the reionization transition. In ΛCDM, the observed polarization pattern corresponds to reionization happening roughly between z approaching 10 and z approaching 6, and finishing by about a billion years after the Big Bang. An older age model has to reproduce the same polarization signature, which means the total column of free electrons along the line of sight and the redshift timing have to match, even if the underlying age in years is very different. Another powerful probe is the Lyman alpha forest in quasar spectra. When you look at very distant quasars, their light passes through clouds of hydrogen gas on its way to us. Neutral hydrogen absorbs light at a particular ultraviolet wavelength called Lyman alpha, so you see a forest of absorption lines. The amount and pattern of this absorption tell you how much neutral hydrogen is left at different redshifts. At high enough redshift, you get almost complete absorption, a Gunn-Peterson trough, indicating a lot of neutral gas. At lower redshift, the absorption is patchy, consistent with an ionized universe with small neutral clumps. These observations already tell a fairly coherent story in ΛCDM. Reionization is mostly done by redshift z approaching 6, and the fraction of neutral hydrogen drops quickly between higher redshift and that point. Any older universe model has to reproduce the same neutral fraction history as a function of redshift. You can reinterpret how many billions of years that took, but you can't change the redshift pattern that the data already give you. That's a hard constraint. So in a 26.7 GY universe, you're essentially saying the redshift window from, say, 15 to 6 covers a much longer time interval in years, but the reionization fraction as a function of redshift still has to look the same in ΛCDM to match CMB polarization and the Lyman alpha forest. That means you have more time in years for stars and galaxies to do the job, but the way ionization progresses with redshift still has to be tuned carefully to fit observations. The real wildcard for this whole discussion is 21-centimeter cosmology. Neutral hydrogen emits radiation at a wavelength of 21 centimeters. As the universe expands, that line gets redshifted, and by mapping it across different frequencies, you can trace neutral hydrogen across cosmic time. Future and upcoming experiments, big radio arrays on the ground and in space, aim to build 3D maps of this signal. That will effectively give us a movie of the cosmic dawn and reionization. When the first sources turn on, how quickly they carve out ionized bubbles, how those bubbles grow and overlap. If those 21-centimeter maps show a reionization history that is squeezed tightly into the timeline that ΛCDM predicts in terms of redshift behavior, it will back up the standard picture and leave little room for radical changes in the expansion history that would push ages around too much. But if they reveal that reionization evolves in a way that can't easily be reconciled with ΛCDM, especially when combined with other probes, then models with stretched age mappings and modified gravity could look more attractive. Either way, reionization is another arena where a 26.7 GY universe has to perform at least as well as the standard model. It's not enough to say extra time makes early stars easier. The model has to reproduce the detailed pattern of when and how the fog lifted, as encoded in CMB polarization, quasar absorption, and eventually 21-centimeter data. And remember, all of this is happening while JWST is still finding more high redshift galaxies and refining the early universe story. So while some people push on the cosmology itself, a lot of others are focusing on the more conservative move. Adjust the messy details of galaxy formation inside ΛCDM and see if that's enough to tame the impossible galaxies before we rewrite the whole cosmic timeline. Which brings us to the next big fork in the road. Do you first try to fix the astrophysics of galaxies within the 13.8 billion year universe, or do you commit to changing the universe's age and gravity? Most astronomers are firmly in the fix the galaxies first camp, and there are good reasons why. What do you try to fix first? The recipe for making galaxies or the entire universe they live in? Most astronomers pick the first option without hesitation. The conservative instinct in cosmology is simple. Before you touch gravity or rewrite the age of the universe, you attack the messy parts, the astrophysics happening inside galaxies. Things like how efficiently gas turns into stars, how feedback from supernovae and black holes regulates that process, what kinds of stars form in the first place, and how dust absorbs and re-emits light. All of that is complicated, full of uncertainties, and absolutely ripe for revision as new data comes in. So when JWST shows you too early, too massive galaxies, the default reaction is our galaxy formation recipes are probably off. In other words, maybe the problem is what we're putting into the simulations, not the underlying ΛCDM framework that sets the expansion history. Think about star formation efficiency. In nearby galaxies, only a small fraction of the cold gas available actually turns into stars per dynamical time. A lot of gas gets stirred, heated, or blown out by feedback before it can form stars. But in the early universe might be different. At high redshift, gas densities are higher, halos are more compact, and metal content is lower. Under those conditions, it's plausible that gas could cool faster in some halos and collapse more efficiently. One mainstream idea is that the first generations of stars, usually called population 3, might have been much more massive on average than stars forming today. Massive stars live fast and die young. They pump out huge amounts of UV light, drive strong winds, and explode as supernovae that enrich their surroundings quickly. If a significant fraction of early star formation goes into massive stars, you can get rapid enrichment and high luminosities without needing billions of years. Once metals build up, star formation might become very efficient in certain halos, pushing galaxy masses up rapidly. On top of that, simulations can adjust feedback prescriptions. Maybe supernova feedback in low-mass, high-redshift halos is less effective than we thought. Maybe early black holes form earlier and grow in a way that boosts rather than throttles star formation for some period. All of these are knobs inside ΛCDM that can be turned to see if you can match JWST's bright, compact galaxies without changing the cosmic timeline. Then there's the observational side. When we say a galaxy at redshift 10 has a given stellar mass or age, that number is not measured directly. It's inferred from the galaxy's spectrum and brightness in a few filters, run through models of stellar populations. Those models assume a particular mix of star ages, star masses, metallicities, dust content, and star formation history. If you assume the wrong mix, you can misestimate the mass by large factors. Add more dust, and the galaxy might be intrinsically less luminous than you thought. Change the assumed distribution of star ages, and the inferred mass changes. Assume a different initial mass function, the distribution of star masses when they form, and the total mass needed to produce the observed light shifts. At high redshift, all these assumptions are on weaker footings because we're working at the edge of what we can see and calibrate. So some researchers argue that at least part of the impossible galaxy problem is us misreading the light. As better JWST observations come in, with more wavelengths and higher signal-to-noise, and as models of stellar populations at very low metallicity improve, some of those extreme mass estimates may come down. A galaxy that first looked like it had, say, 100 billion solar masses worth of stars might get revised to 30 billion or 10 billion. That's still impressive, but much less threatening to ΛCDM. You also have selection effects. JWST early surveys focus on small, deep fields and often pick out the brightest, most extreme objects because those are the ones you can detect first. That naturally biases you toward the outliers, the most actively star-forming and most massive galaxies relative to their peers. Once larger, more representative surveys are done, the population might look more modest overall, and the most outrageous cases might stand out less sharply against the average. So the mainstream program looks like this. Keep ΛCDM as the background, refine star formation models, feedback, and black hole growth, improve stellar population modeling and dust corrections, get more and better JWST data, and see whether the early galaxy problem shrinks. This is already happening. Some initial "this breaks cosmology" claims have softened as new analyses suggest the tension is less dramatic than first thought, or that reasonable adjustments inside ΛCDM can accommodate the objects. But that doesn't mean the radical ideas are pointless. Alternatives like Gupta's 26.7 billion year universe serve an important role, even if they never become the standard. They force us to map out the edges of what's possible. They make the community ask, exactly how far can we push galaxy physics inside ΛCDM before we hit a wall? They highlight which observations are really driving the tension, and which might be explained by local fixes. And there's a deeper point here. The fact that serious papers can propose doubling the age of the universe and still fit major datasets tells you something about where the uncertainties really live. It shows that even a very successful model like ΛCDM might not be the only way to arrange the same observational facts if you're willing to change the underlying rules. It doesn't mean we should throw out ΛCDM casually, but it does mean the foundations of cosmology are not beyond questioning. So even if the final story turns out to be ΛCDM survives and the early galaxies are just extreme but explainable, the path we took to get there will have explored a lot of wild territory: tired light, evolving constants, older universes, and more. Those excursions help us understand why the standard model works as well as it does, and where it might someday crack. And that sets up the next natural question. Given all these moving parts, how is the broader cosmology community actually reacting to the 26.7 billion year idea? Are people persuaded, skeptical, or somewhere in between? And what specific technical issues are most likely to make or break this older universe model? How do working cosmologists actually feel when someone shows up and says the universe is twice as old and you don't need dark matter or dark energy? Short answer: curious, but very skeptical. First, the mood in the field. Nobody has dropped the 13.8 billion year age just because a few papers suggested 26.7 billion. The standard ΛCDM model is still the benchmark almost everyone uses day to day. When people run simulations, interpret CMB data, or design surveys, they're using ΛCDM parameters. Gupta's proposal lives in the interesting, speculative category. Worth reading, worth testing, absolutely not ready to displace the standard model. Most experts treat it as one of many alternative cosmologies that pop up whenever tensions appear, like the Hubble tension or the JWST early galaxy puzzle. They'll say, okay, clever idea, let's see if it survives contact with all the data. The more dramatic parts, like claiming you can get rid of dark matter and dark energy, are where people draw a hard line. Those are enormous claims, and everyone expects extremely strong, multi-pronged evidence before they even think about changing the consensus. Then you get into the technical objections, and they're pretty specific. One big concern is whether Gupta's CCC plus tired light framework really matches the cosmic microwave background and large-scale structure at the same precision ΛCDM does. Planck's CMB data, galaxy surveys, and lensing measurements give you constraints that are not just rough, they're tight down to small scales and detailed peak structures. ΛCDM has been tuned and tested against that years. For Gupta's model, most of the detailed quantitative work so far has focused on supernovae, BAO distances, and JWST galaxies. People want to see a full-blown comparison to the entire CMB power spectrum, polarization data, and the measured matter power spectrum before they take it as a serious competitor. Another technical sticking point is the tired light component itself. Classic tired light ideas failed because they didn't match the observed time dilation in distant supernovae and quasars. In an expanding universe, light curves of high redshift supernovae should be stretched by a factor of roughly 1 plus the redshift, and that's what we see. Quasar variability also shows redshift-dependent stretching. If part of redshift is now coming from photons losing energy rather than expansion, you have to be very careful not to break that time dilation behavior. Critics worry that adding a tired light term risks exactly that, unless it's finely tuned so that all the timing signatures still look like pure expansion. Varying couplings raise more red flags. There are already tight experimental limits on how much fundamental constants can change with time. Atomic clocks on Earth compare different transitions and look for tiny drifts. Quasar absorption lines at different redshifts give you constraints on how the fine structure constant and other quantities could have varied over billions of years. Big Bang nucleosynthesis ties the values of couplings in the first minutes to the observed primordial elements. Any model that lets coupling constants evolve has to stay within those bounds. If the couplings change too much or in the wrong way, you'll mess up atomic spectra, nuclear reaction rates, or the delicate balance that produce the light elements. So, a lot of the technical criticism is basically show me the numbers. Show that your evolving couplings don't violate existing constraints. Show that your tired light term doesn't break time dilation. Show that your CMB and large-scale structure fits are as precise as ΛCDM, not just roughly okay. Until those detailed checks are done and passed, people are going to treat the model as an interesting exercise, not a new standard. There's also a more conceptual complaint. Tuning. When you introduce both varying couplings and a tired light component, you give yourself a lot of freedom. You can change how the expansion rate depends on time, how redshift builds up, and how gravity behaves. It becomes easier to adjust those functions until the model fits the datasets you care about. Pantheon plus supernovae, BAO distances, and JWST galaxies. Critics worry that this starts to look like a fit the anomalies machine, rather than a theory driven by a clean underlying principle. Cosmology has seen similar stories before. Models that add extra parameters to relieve one tension, then more parameters to fix the side effects, and eventually end up more complicated than ΛCDM without clearly doing better overall. The community has learned to be wary of explanations that rely on stacking new freedoms on top of each other, unless those freedoms lead to strong, successful predictions. And that leads to the healthiest part of the reaction: skepticism as a built-in safety feature. Challenging the standard model is not just allowed, it's part of the job. People are supposed to poke ΛCDM and see where it creaks. But the bar to replace it is extremely high, because ΛCDM already explains so much with comparatively few parameters. To dethrone it, an alternative needs to do at least 3 things: match all the current precision data at least as well, solve real tensions in a way that doesn't just amount to parameter hacking, and make new predictions that can be tested and potentially falsified. Right now, the 26.7 gigayear idea doesn't meet that standard. It's intriguing, it's creative, and it usefully highlights where our assumptions sit. But as far as the consensus goes, the age of the universe is still about 13.8 billion years. The ΛCDM framework remains the working model, and Gupta's universe is seen as an outlier proposal that needs a lot more testing. That doesn't make it worthless, it just means we're in the early stages of seeing whether this direction reveals something deep or ends up as one more clever but temporary detour. And that brings up a bigger question. When you've got competing models that can all be bent to fit the current data, how does science actually decide which universe wins? How do you actually decide which universe is real when several models can all be bent to fit the same data? This is where the way science works really matters. First, prediction versus postdiction. Postdiction is what happens when a model looks at data we already have and says, I can explain that too, after the fact. A lot of alternative cosmologies live there. They see the Hubble tension or the JWST early galaxies, and they're built specifically to fix those problems. You adjust equations, add new terms, and then show you can pass through the known data points. Prediction is different. A model sticks its neck out and says, if I'm right, then in future data you will see this specific pattern that the old model cannot reproduce or really struggles with. That's the gold standard. You then go collect new data and see who's right. Right now, ΛCDM has already scored some big prediction wins historically. Accelerated expansion visible in supernovae, the detailed shape of the CMB power spectrum, the existence and scale of BAO signatures in galaxy clustering, and the approximate abundance of galaxy clusters. It didn't just explain those after the fact. In many cases, it predicted them or their general features before measurements improved. Gupta's 26.7 gigayear universe so far is mostly in postdiction mode. It says, given JWST's early massive galaxies, the Pantheon plus supernovae data, and BAO distances, here's a way to reinterpret them that eases some tensions and yields an older universe without dark matter or dark energy. The key question is, can this model move beyond retrospective fitting and make clear, falsifiable predictions? For example, could it say something like, JWST should find a specific evolution of galaxy sizes versus redshift that ΛCDM can't match? Or future 21-centimeter maps should show a certain reionization history that differs in a measurable way? Or strong lens time delays should yield a precise H0 value that favors this model over ΛCDM. Until you have those clean, risky predictions on the table, and they actually work, a model stays in the interesting alternative category instead of becoming a serious replacement. Then there's the question of simplicity, which in Bayesian terms you can think of as a built-in penalty for complexity. Every parameter you add is a dial you can turn to better fit the data, but it also makes your model less economical. ΛCDM looks surprisingly simple for something explaining the entire universe. A handful of parameters describing the densities of ordinary matter, and dark energy, plus a few describing the initial fluctuation spectrum. That small set reproduces a huge amount of data at once. A model like CCC plus tired light comes with more moving parts, evolving coupling constants, functional forms for how they depend on the scale factor, a prescription for how photons lose energy, and a modified expansion history. More parameters, more functions, more freedom. In Bayesian thinking, that's fine only if you earn it. You have to do noticeably better at explaining the data, or explain new phenomena that ΛCDM can't to justify that extra complexity. If all you can say is, I fit the same data about as well as the simpler model with more knobs, the simpler model wins. Next, independent tests. Robust cosmological models aren't just tuned to one class of observation. They get hammered from many directions. CMB temperature and polarization, BAO, Type Ia supernovae, galaxy clustering, weak lensing, cluster counts, Big Bang nucleosynthesis, local gravity measurements, and constraints on changing constants from atomic clocks and quasar spectra. ΛCDM has been through that gauntlet for decades. It has issues, but overall, it passes an impressive number of tests. Gupta's framework has so far been worked out in detail mainly for a subset of observables: supernovae, some BAO constraints, and the early galaxy redshift size brightness puzzle. There's still a lot of work to do to see whether the same model, with the same parameters, can handle the full CMB power spectrum, polarization, cluster counts, weak lensing signals, structure growth, and all the bounds on varying constants. That same parameters part is critical. You can't use one set of parameter choices to fit supernovae and then a different set to fit the CMB and then claim you have a single theory. A genuine rival has to pass all those tests simultaneously. Until CCC plus tired light is put through that full combined analysis, it stays in the exploratory stage. And finally, the big picture view. Cosmology right now is in what you could call a precision weirdness phase. Our measurements are so precise that small discrepancies stand out everywhere. The Hubble tension, early bright galaxies, oddities in small-scale structure, slight tensions in lensing amplitudes. None of these individually is an obvious signal that the whole framework is wrong, but together they whisper that maybe there's something we're not seeing yet. Some of those discrepancies will probably fade as we understand systematics better, as data improves and as models inside LCDM get updated. Others might sharpen and become clear evidence that a deeper change is needed. The only way to find out is to push both sides. Keep refining the standard model and at the same time, develop bold alternatives that seriously try to match all the data. Most of those alternatives will fail. A few might survive and eventually force a major shift. The 26.7 billion year universe sits in that second category right now, a probe pushing at the edges of LCDM, testing how far you can stretch assumptions about redshift, gravity, and cosmic age while still fitting key datasets. It's not the new default universe, but it is a stress test for our confidence that 13.8 billion years is truly locked in. And that leads to a more personal question. If the universe did turn out to be almost twice as old as you were taught, what would that actually change for us, for how we think about our place in cosmic history and the long-term future of everything? What actually changes for you if the universe turns out to be almost twice as old as you were taught? On a personal level, not much, and at the same time, it quietly changes everything about the story you're living inside. Start with the obvious. Your lifespan is microscopic either way. Whether the universe is 13.8 billion years old or 27.7, your 70 to 100 years barely registers. You're still here for a blink compared to the total runtime. From that angle, doubling the age doesn't suddenly make human life feel more or less important. You're already a rounding error. But what it does change is the shape of the cosmic story you've been told. Right now, in the LCDM version, everything feels very compressed. First stars by a couple 100 million years, big galaxies and quasars by a few 100 million more, the bulk of star formation peaking when the universe is a few billion years old, and then a long, slow tail. If you suddenly say the real age is 27.7 billion years, you're implying that what we thought were early chapters might actually be mid-season. There are entire eras of slow structure growth, star formation, and black hole evolution that we've squeezed into a much shorter timeline. In that older universe picture, there's room for more cycles, more generations of stars before galaxies look mature, more time for chemical enrichments before planets like Earth form, more time for small proto-galaxies to merge, collide, and settle into the neat disks and ellipticals we see today. Emotionally, it changes the feeling from we're relatively early in the universe's story to we might be living in a universe that's been busy for far longer than we realized. Now connect that to the big question everyone secretly cares about. Where does this all go? In standard LCDM, with dark energy as a cosmological constant, the long-term picture is pretty stark. Expansion accelerates forever. Galaxies not gravitationally bound to each other get pushed farther and farther apart. Eventually, most galaxies slip beyond each other's observable horizon. They become invisible because their light never reaches us. Star formation winds down as gas gets used up or locked away. Over absurdly long timescales, stars burn out, remnants cool, and you head toward a heat death scenario, a cold, dilute universe where not much happens. In alternative models where the rules change, evolving couplings, non-standard dark components, or modified gravity, that future isn't guaranteed. If gravity weakens differently, or if whatever is driving acceleration changes sign or fades, you can get very different outcomes. Expansion could slow down again. The universe could approach a state with less acceleration, making distant structures more accessible for longer. In more extreme scenarios, you can even get things like a big rip. Expansion tears apart galaxies, stars, even atoms, or some kind of gentle recollapse far in the future. Those are very speculative, but the point is, once you start playing with the basic rules, the ultimate fate of the universe comes back on the table. A 26.7 billion year universe, especially one that claims to remove dark energy, automatically raises that question. If there is no true cosmological constant, what happens in the long run? Does expansion keep going forever, just slower? Does it change behavior again? The model isn't yet developed enough to give a final, detailed answer, but it forces you to ask whether the standard heat death picture is as locked in as people act like it is. Then there's the psychological hit. If we've misread the age of the universe by almost a factor of 2, what does that say about our confidence in our best theories? It's tempting to hear that and think, so our models were useless. But that's not how science works. If something like a 26.7 billion year universe turned out to be right, it wouldn't mean all the previous work was pointless. LCDM would still have been an incredibly successful approximation that organized decades of data and led us to the edge of the next theory. We'd keep it in the textbooks as the model that got us 90% of the way there. The same way Newtonian gravity is still incredibly useful, even though we know general relativity is more accurate. The real lesson would be this. Even when we're deep into precision measurements and fancy statistics, our understanding can still be fundamentally incomplete. We can be almost right in a way that still leaves room for the universe to surprise us on huge scales. That doesn't show weakness, it shows that the method is robust enough to overturn its own conclusions when new evidence demands it. You refine, you question, you update, and sometimes you replace. That's the point. And through all of this, early galaxies, Hubble tension, cosmic age debates, one thing does act like a constant in practice: curiosity. Every time a new telescope comes online and finds something that doesn't fit, it gives us a new puzzle. JWST shows up, and suddenly we're arguing about whether we underestimated galaxy formation, misunderstood distances, or misjudged the universe's age itself. People dig into data, invent new models, attack old ones, and design better experiments. That drive to keep asking, wait, are we sure, is the real engine behind all of this. So whether the final answer is 13.8 billion years, 26.7 billion years, or some third number nobody's proposed yet, the important bit for you is that you're living in a moment where we can even ask that question seriously. We can see galaxies from when the universe was tiny, compare models that reshape cosmic time, and argue with actual evidence about the age of everything. And that brings us to the last step of this story. Where do we go from here? What observations in the next decade are actually going to decide whether ΛCDM bends, breaks, or just absorbs these tensions, and whether a stretched, older universe really has any chance of stepping into the mainstream? So where does this all actually go from here? Who's going to decide whether the universe really is 13.8 billion years old or something as wild as 26.7? Over the next decade, a whole army of experiments is going to squeeze the room for exotic ideas. JWST is just getting started. Future deep surveys will push to even higher redshifts, get better spectra, and measure not just, hey, there's a galaxy, but detailed properties, stellar populations, metallicities, dust, and kinematics. If the early universe galaxy population keeps looking impossibly massive and mature for a 13.8 billion year timeline, the pressure on ΛCDM goes up. If, as data gets cleaner, those galaxies slide back into the barely extreme but still okay range, the pressure drops. Next-gen CMB missions will hammer on the early universe. Projects like Simon's Observatory, CMB-S4, Lightbird, and others are designed to measure polarization and small-scale anisotropies far more precisely than Planck. They'll check whether the acoustic peaks, lensing signatures, and polarization patterns line up perfectly with ΛCDM, or if there are small persistent deviations that could hint at evolving couplings or non-standard expansion. For a 26.7 GYR universe to stay alive, it has to pass that test with the same precision ΛCDM already has. Then you have the massive spectroscopic galaxy surveys. DESI, Euclid, the Vera Rubin Observatory's LSST, and more. These projects will map tens of millions of galaxies and quasars, building a 3D picture of large-scale structure and BAO with much higher accuracy. They'll measure how structure grows over time, how the BAO ruler evolves with redshift, and whether the cosmic web matches what ΛCDM predicts or demands a different expansion history. Subtle differences in growth rate or clustering could either support or rule out models like CCC plus tired light. On top of that, 21-centimeter experiments will target neutral hydrogen directly across cosmic time. Arrays like Hera and later the Square Kilometer Observatory will try to map the 21-centimeter signal from the cosmic dawn and reionization eras. That will give you a frame-by-frame view of when the first stars turned on, how quickly ionized bubbles grew, and how long reionization took as a function of redshift. If those maps scream, this timeline is incompatible with 13.8 GYR ΛCDM, older age models suddenly become stronger contenders. If they fit ΛCDM neatly, the room for extreme alternatives shrinks. And then there are the gravitational wave standard sirens. As detectors get better and more mergers are observed with identified host galaxies, you'll get a new, independent way to measure the Hubble constant and the expansion history that doesn't rely on traditional distance ladders. Combined with better strong lens time delay measurements, this will either sharpen the Hubble tension or smooth it out. Those results will be brutal for any model that tries to fiddle with redshift distance relations, including CCC plus TL. So what would it actually take for a 26.7 GYR universe to move from fringe to contender? You'd need multiple independent probes: CMB, BAO, supernova, structure growth, lensing, 21-centimeter, and gravitational waves all leaning in the same direction and refusing to be reconciled inside ΛCDM, even after you've done your best to fix systematics and tweak the messy galaxy physics. You'd need those data to clearly prefer an expansion history that simply can't be captured by the standard model's limited set of parameters. At the same time, a CCC plus TL style model would have to be fully developed and tested. That means showing that with a single consistent set of assumptions about evolving couplings and tired light, it can reproduce the full CMB power spectrum and polarization, match primordial element abundances from nucleosynthesis, generate a realistic large-scale structure power spectrum and cluster counts, respect bounds on varying constants from atomic clocks and quasar spectra, fit the Hubble diagram from supernova, BAO distances, and strong lenses. If all that lined up and the model also naturally explained early JWST galaxies without extreme star formation assumptions, then you'd be looking at a serious competitor. We're not even close to that point yet. That's the bar. What's more likely in the near term is both less dramatic and more interesting. The most probable outcome is that ΛCDM survives, but not as a rigid, untouchable monument. Instead, it may pick up extensions, maybe a more flexible dark energy sector, maybe a small early dark energy component that tweaks the Hubble tension, maybe some subtle new physics in neutrinos or dark matter interactions. You keep the basic framework, an expanding universe with dark matter and dark energy, but refine the details to absorb new data. Ideas like Gupta's 26.7 GYR universe still matter in that scenario. Even if they don't survive intact, they map out the edges of the parameter space. They show where the standard model could, in principle, be modified. And they force us to understand exactly which observations lock down which parts of the story. They're like stress tests you run on the theory to see where it bends or breaks. So you end up in this weird double state. The boring bet is that 13.8 billion years stays the official age, but the route to that conclusion becomes more nuanced with better data, more careful modeling, and maybe a slightly upgraded version of ΛCDM. The exciting bet is that something in the growing pile of tensions refuses to go away, and one of these radical ideas gets a second life as more evidence stacks up. Either way, here's the real punchline. You've been told the universe is 13.8 billion years old. That might be right, but telescopes are whispering that our cosmic clock could be off by a factor of 2. Whether the final number is 13.8, 26.7, or something we haven't even imagined yet, the real shock isn't the age of the universe. It's that a primate on a small rock can look up, measure ancient photons, argue with Einstein, and dare to ask if reality is older than time itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.